Good morning, everybody. My name is Thomas Gasparotto. I am a PhD student at University of Lorraine in France. And I am going to introduce my research project, which is conducted in a collaboration between CNPP and LEMTA, Laboratory of Energetics and Theoretical and Applied Mechanics. And this project concerns the implementation of an emergency egress model based on a macroscopic continuous approach. So let's start with the motivation and the objective of this study. Our main goal here is the development of a complete egress model, including fire effects on persons and devoted to future years for fire safety engineering. A lot of numerical tools have already been developed to simulate evacuation of buildings, and most of them are such as agent-based model or social force models, are based on a microscopic approach, in the sense that persons are considered as individual entities with own characteristics and whose respective motion is governed by different laws. So these types of model generally provide output data which are significant for a particular initial distribution of persons with input parameters defined thanks to statistical distribution. So this microscopic description generally needs a statistical treatment of output result to provide evacuation times which can be considered as representative for all scenarios likely to happen. That's why our objective here is the development of a model able to provide, by a fast computation, evacuation times significant for a large number of configurations and which do not depend on a particular initial distribution of persons. One of the key features of this model will be the integration of fire stresses in terms of thermal effects and low visibility. The approach we have selected here is a continuous macroscopic approach, which consists in describing a population thanks to global parameters and average characteristics in a continuous space and time. In the first time, I will detail the assumptions and the formulation for a new evacuation model, with our first results concerning its validation at small scale and comparison with other tools. Then I will invoke the solutions adopted to take into account fire influence on egress condition with an application on a simple test case. Then I will conclude with some perspectives and ongoing developments. So in the approach we chose here, instead of considering people as individual particles, the model tracks the evolution in space and time of a macroscopic quantity, which is people density, or the number of persons per unit area. The pedestrian motion model is based on three fundamental assumptions. First assumption, without constraint, people move at preferred walking speed. Second hypothesis, people density cannot exceed a critical value. And third assumption, flow rates through openings cannot exceed a critical value. From a mathematical point of view, a balance is written for the people density in a pre-calculated velocity field. The equation 1 here is similar to the continuity equation in fluid mechanics, and the equation 2 means that the real speed of persons corresponds mathematically to the projection of their preferred working speed on the permissible velocity space at least square sense. So it means that the real speed of persons will be necessarily lower than their free walking speed due to the presence of other persons. A finite volume method is used here to solve numerically the problem in a two-dimensional computational domain, which is considered as a square mesh grid with three types of cells. We have the wall cells, the black cells, which are the physical obstacles which cannot be entered by people. We have the available cells, the blue cells, which are the the space available for motion of persons, and the exit cells, the red cells, which refer to the outward exit openings. So the pedestrian motion model needs also the introduction of four parameters, which are the preferred walking speed, the reaction time of persons, which is variable according to the risk perception, the critical people density, which is generally estimated at 5 persons per square meter, and the maximal flow rate through exits. I have estimated it at 1.1 person per square meter for a 1 meter wide exit. I present here the specific algorithm I use to solve numerically the problem, which is divided in 2 main steps. I have called the first step POLO, path-finding algorithm using length optimization. And the goal of this algorithm is to compute the velocity field in which people density will be transported. So after creating the geometry, the POLO algorithm computes the length of the path from each starting point to the nearest exit. It is assumed here that people try to minimize their travel time to the exit, and so have a perfect knowledge of the configuration of the building. So from each point, the evacuation velocity is directed along the shortest path to the nearest exit. I call the second step of the algorithm macroscopic analysis of rescue configuration for optimal evacuation, which consists in transporting people density at preferred working speed with a finite volume method. And this transport of people density can lead numerically to situations where we have a density excess in some cells. So I introduced a corrective step to redistribute the density excess from saturated cells to neighboring cells to satisfy the congestion constraint, the critical density. So this algorithm and its implementation had to be confronted against real data. And as a first validation, I carried out an experience at a very small scale in a very simple configuration, which is a 10 square meter room with a single exit. A GoPro camera was set at the door in order to take evacuation times of persons and to determine at each moment the number of persons who were out of the room. 20 repeated tests were carried out with 10 persons whose initial positions and orientations were randomly chosen and whose characteristics were determined in the preliminary steps. The rate curves on figure 6 here show our experimental results average on 20 tests for the ratio of evacuated persons among time. We can compare it to the green curve, which is the solution computed by our code, taking into account the interaction between people. And I have presented the blue curve, which is the solutions when we consider that people evacuate as if they were alone. So the blue solution does not take into account the interaction between persons. These results highlights 2 main insights. Firstly, validation at small scale seems promising at this stage because the results computed by a single simulation of a mean scenario are similar to those obtained by statistical treatment of 20 repeated tests. And secondly, we can notice that congestion situations are correctly handled. I compared the model to other Egress tools on another simulation case. And the configuration I have used for the comparison is the one described in test 9 in Annex 3 of evacuation guidelines for analysis of new and existing passenger ships of International Maritime Organization. It consists here in a 600 square meter room with 4 1 meter wide exits, with an initial population of 1,000 persons uniformly distributed in the room. The table 1 shows a comparison between our results and some results extracted from literature for different egress tools. So we can notice that different egress times are included in a very large interval, and that our model provides an evacuation time which is included in this interval. So at this stage, we can consider that the results are coherent with other models. So I talked about our pedestrian motion model without fire constraints, and now we are going to focus on integration of fire effects into the model. At this stage, 3 different ways are investigated to integrate fire conditions. Firstly, burning cells can be considered as physical as obstacle, which can be entered by people. Secondly, the assessment of tunability in fire conditions needs the introduction of threshold values for tunability criteria. So here are some examples of values I used for the following simulations: 60 degrees for temperature, 2.5 kilowatt per square meter for heat flux, and the critical extinction coefficient, which correspond to a critical visibility distance of 10 meters, according to the regulations established by Tadeusz Jeans for evaluation of visibility in fire smoke. So cells with constraints above these thresholds can be considered as blocked cells. And thirdly, I consider that local extinction coefficient of smoke reduces working speed of persons according to a linear relation. I notice here that the fire-related data are updated at each time step and are extracted from the last version of Fire Dynamics Simulator. As a test case, we are going to focus on the test number 10 described in the guidelines for evacuation of International Maritime Organization. In this test, the configuration consists in a group of 12 boat cabins separated by a corridor. The domain is 18 meters long for 12 meters large. And to create penalizing fire conditions, I added a fire source in one of the cabins, whose nominal heat rate is 1 megawatt, with a medium growth according to NFPA 204 standard. In this configuration, 23 persons evacuate the domain with a uniform reaction time of 30 seconds. You can see here on this figure example of evolution of fire constraints 2 minutes after beginning of fire, and the red zone, which correspond to blocked zone. So it is the zone where the cells where the fire constraints are higher than the critical values. From this scenario, I decided to compare our model with EVAC, the evacuation module embedded into Fire Dynamics Simulator, and we used the same input parameters to make the comparison appropriate. Fire-related data were extracted each 5 seconds, and I programmed a conservative behavior for agents in EVAC. Conservative behavior is one of the particular submodels embedded into EVAC. And 50 simulations were run with EVAC to collect average data. The figure here show the ratio of evacuated persons among time with EVAC, with the blue continuous line is the average for the 50 simulations, and the red curve is the solutions computed by our code. The table 2 here represent a comparison between codes of intermediate egress times. So, for example, T50% is the time at which 50% of the population has evacuated the domain. We can see from these results that the comparison, the results are similar for both codes, even if we are more optimistic for egress times with our approach. But at this stage, the discrepancies can be explained by the different assumptions made in behavioral models, because I have assumed here that people minimize their travel time according to the distance to the exit. And the assumption made for evac is a little bit different, because I have attributed preference for exits for people. But at this stage, we can consider that this comparison between codes are promising and reveals a good agreement for egress times. To conclude, I presented a new evacuation model based on a macroscopic continuous approach, which was validated at a very small scale and compared with other egress tools. And fire effects were taken into account, considering threshold constraint and penalize the velocity. I notice here that this macroscopic continuous approach is particularly innovative, because up to now and to my knowledge, this type of model has been the source of a lot of mathematical and theoretical studies, but was not yet investigated for a practical application with integration of fire. And we saw that our model is able to provide evacuation time significant for several particular scenarios with a single simulation of a mean scenario with average input parameters. I will conclude with some perspective and the ongoing research, which will improve the reliability of this model. First point is a better way to integrate fire influence on egress conditions. I have assumed here that fire has no impact on egress conditions under critical values. This hypothesis is quite strong and can be made more realistic, considering, for example, several levels of constraint. Second point is the relevant integration of visibility as a decision-making process. And this feature will allow the integration of exit signage into the simulation to compute the evacuation velocity, for example. The third point is the integration of several types of populations in the same simulation. So several types of population who have different characteristics or different behaviors or different exit preferences. The fourth point is the estimation of pre-evacuation times. I have not mentioned in this presentation pre-evacuation times, but it is a crucial point for assessment of evacuation times, because it can be longer than the travel time to exit. And the last point is the validation against real data extracted from evacuation drills. I have already organized evacuation drills in a university in Nancy in France at a medium and large scale, and I hope the exploitation of this data will enable the validation of this tool. Thank you for your attention.
Check. Hi, Thomas. Thank you very much for that. It was really interesting. I have about 100 questions, so I hope we can chat at lunchtime. But just two to get started with. So the first one I had was about the small test that you did in the room. So how were the free walking speeds calculated? Because 0.7 meters...
The free walking speeds were determined experimentally in the same condition than the experiences. So the occupants evacuated the room alone, so I made the same experience for each person with one person.
Okay, so it was in a 10-meter room?
Yes.
And that averaged as 0.7 meters per second? That seems very low for young, healthy people.
You say that?
So I saw the average was 0.7 meters per second, ish, and that seemed rather low. But I mean, we can discuss that again. Yes. I'll ask my second question to move on. In terms of the pre-evacuation time, is it possible to put a distribution in? It seemed that there was just a mean, but it's well established that there's a sort of log normal distribution of pre-evac time. So a suggestion, I guess, for a development might be to incorporate that.
It is a good question. My idea is to create a field of pre-evacuation times, which will be correlated to the constraint of fire. So. My idea is to correlate the local reaction time with the fire constraint, but it is not necessarily the best way, because we have some more complex behaviors. For example, the ailing behaviors. The people will follow the first person who evacuate, and so I don't know if it will be the best way, but it's sure that it is a crucial point.
Brilliant, thank you very much. Thanks.
Neighbor, another question. I want to discuss a bit, probably get some figure for you. Why do you think macroscopic models are not used in fire safety engineering? Because I've been in a couple, actually early this year, I've been at a conference in applied mathematics, and I've seen many of these models. And I thought the reason why we don't use this in fire safety engineering is because we generally work with the way lower densities. So we look at scenarios in which the individual behaviors matters a lot. Do you want to give me a comment on this? What do you think, how your model will work with very low densities in which the behavior of individuals may have an impact?
Yes, these types of models are generally used with very high densities, and so it is an innovative point. But we saw, for example, on the simulation of the test number 10, I present for the comparison between the comparison between our code and evac for the integration of fire conditions. We saw that the model was able to provide evacuation times who were similar that those obtained with microscopic approaches. So I think it's a very good question. And I don't see why this type of approaches would not be efficient with low densities.
Because, for instance, I mean, you can have a couple of, let's say, agents in microscopic models that you may want to do something that can have a significant impact on the final total evacuation time. So this assumes basically that you have people moving from point A to point B, which is an assumption that many models use. But if you want to have more complex rerouting, counterflows, how will you solve counterflows with this, for instance? Like counterflows?
Yes, as...
Do you know what I mean? Yeah, this kind of more complex.
Yes, it is one of the points I have to investigate in. Because I talked about the model with several populations, with, for example, different exit preference, and we would have to handle the case of the counterflow. So my idea at this stage is to consider that the speed for one population who have chosen one exit is affected by the presence, the density of the population who are going in the other sense. But these types of approach has to be validated, and it is one of the investigated points. If you want, we can talk about it at the next coffee break, but it is a very interesting point.
Definitely. Thanks a lot.
Anyone else? No? Okay, well, thank you very much.